Okay, we're going to do a couple of examples here. I think we'll get two in on this one video. Uh, so this is what we want to do is come up with differential models based on the perturbation variables. Okay, so we have a tank that's drawing from a pond at atmospheric pressure, sucking up water. Q, so here's the uh, pump curve constant that we would use. This will then be stepped up to some provide some flow rate through here. We have an open top tank, capacitance C1, pressure on the bottom P1. That will result in flow rate omega 1 coming out. Then we go through this valve, which has a pump characteristic. We'll just call it R1. It has K1, but that produces R1 when we linearize it. And so we're going to go from P1 pressure drop down to P2. Then, and so some can get stored here. So that creates omega 2 here, which goes to a valve that is just jumping out, dropping down onto ground, atmosphere, to a pond, what have you. And here we have this valve is set to the same. This is R2. K2, R2. All right. So we have all of the stuff relative to being linearized. We're just going to go directly to the perturbation variables. Okay? Okay. So everything's to be linearized here. So we're just going to have one, this will be at steady, and it will do everything at steady state. So the pump flow is omega 1, is omega 2, is just generic omega. Okay, so let's look at this first tank here. So we have C1, P dot, but it's the perturbation version, but that's fine, will be the flow in, perturbation flow in minus perturbation flow out. Omega P hat minus omega 1 hat. That's all we have to do. Okay, now we do have to go, well, what is omega P? All right, well, that'll be driven by pressure, but from here to there, so we are stepping up the pressure, but it's from 0, okay? We're just looking with gauge pressure, so the steady state we don't care about. So we're going from 0 to P1 hat. And then here we have our Q, it's minus 1 over Q. This is the input. Then we subtract off omega 1. Okay, so that's where that minus sign comes from. But then this will become 1 over R, P1 minus P2. We'll be dropping in pressure. That's what will create that flow. Okay, and so we're going from P1 hat to P2 hat. Then we have another tank. So we'll just, every time we see a tank, it's like every time you see a mass. So here we have C2, P2 hat dot equals, we have the flow in. 1 over R1, P1 minus P2, minus, we have another valve here, R2, minus 1 over R2, P2 hat. But it's going out to atmosphere, so that's just constant. We're not looking at the static terms have been eliminated to create a dynamic differential equation. Make that a little easier to see. And we're all done. So we have the next problem. Let's move this up a little bit, give ourselves a little more room to see things. And so I have a source here that's supplying liquid into tank 1. And it's so we have C1, C2, C3 with their individual levels, creating individual pressures. So P1 hat, P2 hat, P3 hat. And there are valves in between. They're all set to the same spot, and they're all identical. So we have R, 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 and then we have omega O output flowing out. Want to model this? Okay. We have an equation for every tank, just like every mass. All right. So we have C1 P1 hat dot, okay, the derivative equals a flow in minus flow out. Well, flow in, we'll take the perturbation flow, boom, minus 1 over R, P1 hat minus P2 hat, and then minus flow leaving, we're assuming it's leaving, 1 over R, P1 minus P3 hats. All done. Pump, or tank 2, we'll assume it's flowing from here and then out. If we're wrong, then this pressure will be higher and that would backflow for some reason. All right, so we have C2 P2 hat dot equals flow in, okay, 1 over R, it's positive here, it's flow in, P1 minus P2 hat. We'll assume this flow is out, minus 1 over R, P2 minus P3. Boom, done. Now we'll go to the final one, final tank. We're assuming everything's coming in. So the flow in would be 1 over R, P1 minus P3 hats, and 1 over R, P2 minus P3 hat. Make that easier to see. And then this is the one leaving, minus omega output hat. All done. Easy. So if we're really stressed about all the linearization, once you linearize everything, as these show, it's really all just common sense. And it flows very nicely. You go to all of the tanks and you simply write very logical equations, and you simply know how to use these linearization factors. The pump constant, the valve constants, and you're there. I have one last problem, and we're done. I'll see you soon.